Okay, guys, we're going to take the time to revisit the Pythagorean Theorem today. Pythagorean Theorem simply says that in a right triangle, the square of the hypotenuse is equal to the sum of the square of the legs. The thing that we would know, or that you would remember, I guess, would be the idea that the formula comes out of it here, which simply says that a squared plus b squared is equal to c squared. If we look at what the theorem actually says, it's an if-then statement. So if I have a right triangle, the conclusion is that the a squared plus b squared is equal to c squared. So that being said, if I'm trying to prove this, which is the reason we're revisiting it right now, is we would have to start out with the hypothesis as our given information. So if I have a right triangle, then we should be able to conclude at the end of our proof that the a squared plus b squared is equal to c squared. So to set the proof up for this, we're given this triangle ABC with legs A and B and hypotenuse of C. So we've got our right triangle, and we're going to prove that the a squared plus b squared equals c squared. And to do this, we're going to use this theorem from the last section that says the leg of a right triangle is a geometric mean between its projection and hypotenuse. So here we go. Let's dig into the proof. The first thing I did here is I drew the diagram of the right triangle ABC. I've labeled the legs A and B. I've also labeled the projections as X and Y and the hypotenuse as C. So the first step of this is using that theorem that we talked about, that each leg of a right triangle is a geometric mean between the hypotenuse and the projection. So here the leg B is a geometric mean right here between its projection of X and the entire hypotenuse of C. And likewise here, this proportion comes from the other leg of the Papa Bear triangle. This leg of Papa Bear is a geometric mean between its projection at Y and the hypotenuse, which is the whole length here of C. So A is a geometric mean between Y and C. Then in my next step, to go from here down to there, I simply take this proportion, and we know the product of the means is equal to the product of the extremes. So yes, back in your younger days, you called that cross multiplying. Now we use the big boy, big girl terms of big product of means equaling product of extremes. Well, from this step here down to my next line right there, we take the left side a squared and b squared, and what did we do with those to get this? We added them. And likewise here, I took the cy and the cx, and over on this side of the equal sign, we added them. So we basically just took those two equations, we added them together. That's addition. Back in your algebra days, if you had a common factor of c, you would factor that c out of each term. So you're factoring out, and what's left then when you divide by c, you get x, and you divide by c here, you're left with plus y. We don't really have the factoring property, if you will. It's the reverse of the distributive property. But so by substitution, we just know this from algebra that those are equal, and so I'm just replacing something of equal value. Well, I'm getting really close here. I have a squared plus b squared equals c times x plus y. Well, what is x plus y? Right here, I have x. Right here, I have y. And if I take the length of x plus the length of y, it gives me the length of c. So I can get rid of this. I can put c here in its place. So that really gives me c times c, which is c squared. So in the end, I started out with a right triangle. Now I conclude that the a squared plus b squared equals c squared. So essentially, that is your proof of the Pythagorean theorem. That is one of many ways to prove it. Presidents of the US have come up with original proofs for the Pythagorean theorem. So that is just one of many different ways, the most proven theorem of all. Taking a look at some examples here, a little bit of a review of things we talked about in the last lesson here. We have the big Papa Bear triangle, we have the Mama Bear and the Baby Bear triangle, and we had these proportions that came out of it. And the first one said that the altitude was a geometric mean between the segments of the hypotenuse. So, and then I also had the one that talked about the leg of Papa Bear was a geometric mean between the projection and the entire hypotenuse of Papa Bear. Remember when they're talking about that with the leg, they're talking about the legs of Papa Bear. They're not talking about the legs of Mama or Baby Bear. All right, that being said, if I look at my first example, the dilemma that you're going to run into here is when do I use each of these? Well, you've got to kind of look at what you have. If I look here, I'm asked to find x. I've got this length of 10 and I've got this length of 5. And well, x in this diagram is the altitude. So I'm going to lean toward this one already just because of that. And the altitude is a geometric mean between the two segments. And oh, yes, I do have the two segment lengths here. So x, the altitude, is a geometric mean between the two segments of 5 and 10. So then we solve this, and we know that x squared is equal to 50. And we take the square root on each side, and as I take the square root, my x value is going to be equal to 5 radical 2. Okay, likewise, what to use when? I just kind of know these theorems kind of in my mind. I don't really have those formulas memorized. I don't necessarily have this proportion or these guys here memorized. I just say in my head, y. Y is a leg of Papa Bear. And the y, the leg, is a geometric mean between the projection, ooh, I've got that, that's 10, and the entire hypotenuse of Papa Bear, which is the full length here of 15. I have enough information because I only have the one unknown. Y, the leg of Papa Bear, is a geometric mean between its projection of 10 and the entire hypotenuse length, which happens to be 15. So if I start solving this, the product of the means gives me y squared, the product of the extremes gives me 150, and as you take your square root in simplest form, the square root of 150 breaks down into 5 radical 6. So final answer there, 5 radical 6. Throughout this chapter, I'll be very consistent. If you have a radical in your answer, you do not want to give me the decimal. I want the simplest radical form. So here we go. Taking a look at my next one here. I've got the altitude. So I'm determining, can I use one of these? Well, the altitude is a geometric mean between the segment of 6 and this segment here. Okay, I could use it, but that's not helping me find z. The other one, the leg of Papa Bear, well, z is a leg. Z is the geometric mean between the projection and the entire hypotenuse. 2 more unknowns there, so that's not going to really help me so much. So as I'm looking at this, I say I got 6 and 8, and this kind of ties into where we're at right now. In this little baby bear triangle, talked about the Pythagorean Theorem today. I can use the Pythagorean Theorem to find out that this length here is 10. A squared 36 plus 64 is equal to the c squared, if you will. And as I'm looking at this, once again, these still don't really apply. But what I'm seeing here is that I have all the side lengths of Baby Bear. And we know these 3 triangles are similar from that theorem that we had at the beginning of the last lesson. So if I looked at comparing maybe Baby Bear to Papa Bear, maybe I can come up with a proportion here that would help me out. Well, Baby Bear to Papa Bear, 6 is a side length of Baby Bear. And keeping it simple, 6 is the shorter of the 2 legs here of Baby Bear. So this is going to be comparing short leg of Baby Bear to the short leg of Papa Bear. Well, Papa Bear, his short leg is 10. And that's equal to, well, another side that I have here, I have all the sides of Baby Bear. The only other side I have of Papa Bear is this side here, and of the big Papa Bear triangle, that's the other leg. It's the long leg. So in my other proportion here, or my other ratio of my proportion, I'm going to compare the long leg of Baby Bear, which happens to be 8, to the long leg of Papa Bear, which is z. So I've got these similar triangles using Baby Bear compared to Papa Bear to set up a proportion here, and 6z is equal to 8 times 10, which is 80. When you divide here, you're going to divide by 6, and z ends up equaling, reduces down to 40 over 3. That's probably your best answer because that's perfect, or that is approximately equal to, 3 would go into 40 13 times. It'd be 13.3 repeating. And if you're putting answers into the computer on worksheets, I don't want things any further than to the tenths, so you can just leave it as 13.3. To me, though, the best answer here would be 40 over 3 because that's perfect. There's no rounding error. There's a rounding error in 13.3. All right, taking a look here at our last example. It's got some side lengths here of Papa Bear. I look at those ideas of, all right, the leg is a geometric mean between the projection and the hypotenuse. Well, I don't know the projection and I don't know the length of the hypotenuse, so 2 unknowns is not good for my proportion. Once again, here's a leg of 12. It's a geometric mean between this projection and the entire hypotenuse. Once again, those are both unknown. So in my mind, as I'm looking at this, I'm thinking maybe what I can do is Pythagorean theorem to get the length of the Papa Bear's hypotenuse to help me write that proportion. So let's give this a quick go. All right, so a squared plus b squared equals c squared. So a squared of 64 of Papa Bear plus the b squared of 12 squared, which is 144. And that is equal to c squared. 64 144 gives me 208. That's equal to c squared. Let's see, the largest perfect square in 208 is going to be 16. So when I take the square root of 208, I should simplify into 14 radical 13. So now I know that the hypotenuse here is 4 radical 13. So at this point, I don't know that it really matters which one I look at, but I'm going to take a look at this leg here of 8. 8, the leg from those proportions we have from last class, from last lesson. The leg of Papa Bear is a geometric mean between its projection, well, the projection is W, and the entire hypotenuse of 4 radical 13. Well, 4 and 8 are both outside the radical. Those can reduce to 2 over 1. So as I do my math here, I would take the product of the means and extremes, and we would say that radical 13 times W is equal to 8 times 2, which is 16. And then to solve this, I divide by radical 13 on each side. And as I do that, the radical 13s here are going to reduce away. So to simplify this answer in the end, simplest radical form, we should not have a radical in the denominator. So if you remember back in your algebra days, to rationalize a denominator, we multiply the top and bottom times radical 13. And you would have talked about that's just multiplying times 1 because anything over itself is 1. So here I'm left with on top 16 radical 13 over, and then radical 13 times radical 13 is radical 169, or simply just 13. So the length of W in simplest radical form is 16 radical 13 over 13. Okay, guys, lesson was on Pythagorean theorem. As you can see here in a couple of these problems, for instance here, I used the Pythagorean theorem to help me get a length that I needed to get my answer to my question. And likewise here, I used Pythagorean theorem to get this length here of 10, although this was a Pythagorean triple that we've known, relative to root off the 3, 4, 5. This was the 6, 8, 10. So you might not just get questions straight out with Pythagorean theorem. It's going to be things like this where, ooh, I've got that Pythagorean theorem in my toolbox. I need to know when and where I'm going to use it. And so, yeah, if you have two sides of a right triangle and you can use the third one to help you solve a problem, go ahead and use Pythagorean Theorem quick. Anyway, I hope that helps, and hope to see you on the chat. And guys, this is a section, these couple sections here, some time you need to get in and see me for help. I would strongly suggest doing that.